Hi, Seyi.
Hi, Peter.
Welcome to the podcast, Everyday Metallurgy.
Oh, I'm glad I'm here today. We finally made
Yeah,
it.
thank you very much for accepting my invitation. Today, we're going to talk about maybe the top topic right now in the materials world. The hydrogen era is coming up.
Mhm.
And hydrogen is a fantastic atom because you can transfer energy in it. It's abundant, it's all over, but it's also so small that it can penetrate even a dense wall.
Mhm.
So it can create a lot of problems. So it can save a lot of our problems in the world, but it can also create the same amount. And we might not be fully prepared to enter the hydrogen era. But fortunately, we have people like you looking deeper into how does hydrogen affect our materials and how could we mitigate. So that is what we're going to talk about today. But first, would you give a short introduction to yourself, your background, and where you're working on your daily life?
Okay, thank you very much, Peter. I'm also glad I'm here today. So my name is Seyi, as you know. So I am a material engineer. So I have about 7 years of experience in material design and development. I've worked through smart alloys, shape memory alloys, nickel-based super alloys, and currently I just subscribe into the sustainability world. So
Mm.
I'm working on developing some thermometallic materials for harvesting low-grade waste heat, and
Hmm.
also working on hydrogen direct reduction ion as well.
Hmm.
Um, on the theoretical level,
Yeah.
so to be able to have a kind of an overview of
Mm.
what actually is going on in that field, and also what are the things that needs to be improved when it comes to the research aspect. Yeah, so that's me.
Yeah.
Thank you.
Uh, and where you positioned
Oh,
on?
presently,
Yeah.
yeah, I'm working in the Institute of Material Development in Royal University Bochum here in Germany.
Mm. Perfect. Then
Thank you.
everything is settled. The scene is ready.
Yeah, yeah.
Um, if we start from the top and look at this hydrogen era, uh, why why has it started? Why are we talking so much about hydrogen? What is the purpose? Where are we going to use hydrogen in our future society?
Thank you. That's a very brilliant question because for every technology that comes up, there is always a need for it, right? So if there is no need for it, then we won't do it.
No.
So, and this is also applicable to hydrogen, right? So, when you look at hydrogen, there are so many fields that hydrogen plays a bigger role. So, let us look at, for example, petroleum industry.
Mm.
In refinery, you see what we call a process called hydrocracking. So you bring these bigger hydrocarbons into smaller
Mhm.
networks. So we have our diesel, our fuel, and things like that. And with that process alone, it demands about 22% of the global hydrogen demands production.
Mm.
That's one aspect. We can also use hydrogen to take away some impurities in these hydrocarbons, something we call the desulfurization. So hydrogen reacts with this hydrocarbon and gives a kind of hydrogen sulfide, right? That is to the petroleum side. So let us look at the energy side. For example, we can use hydrogen to balance the energy supply on the grid.
Mm.
There's something very important about renewable energy, in the sense that they are very, very fluctuating. They are not
Yep.
constant. So for example, when you're using wind, if there are no wind, then you will look for something else, right? But when
Mm.
energy comes into place here is that, for example, in the day there are high demands, but in the afternoon there are lesser demands because people
Mm.
have gone to work and things like that. So, but then we're still producing the same amount of energy. So all we can do is to divert some of this energy, some of this production into production of hydrogen. So
Mm.
we produce hydrogen. Hydrogen is an energy carrier, it's not a source itself. So in the evening, where there is high demand for energy, so what we do is to burn this hydrogen to supply energy. So we
Mm.
can use that. We can also use it, for example, in gas turbine, for example, so to ignite the air that comes into the gas turbine, then
Mm.
to produce a kind of a mechanical work that we can use to power some generators and supply some direct electricity.
Yeah.
We can also use it in heavy industries like steel making, for example,
Mm.
especially in these days where decarbonization becomes a thing of a
Mm.
goal of all research, right? So what they want to do is they want to replace CO with hydrogen. So and then this will be done below the melting temperature of iron. So it simply means we need a lot of hydrogens on that as well. So they call it the
Mm.
hydrogen direct reduction iron, right?
Yeah.
So there are so many places. I mean, so many applications of
Mm.
hydrogen, even in our cars, the hydrogen fuel cell, and things like that. In transportation, in shipping, in maritime, also in aerospace as well. I mean, of recent, I heard about it's not like 2 months ago they tested an hydrogen for sustainable air fuel, right?
Mm.
On this airplane for, and then it travels for some kilometers and try to see how it works. So in a nutshell, hydrogen has come to stay. So and then the application is far enormous than what we could think, even
Mm.
in agriculture and also in food processing and things like that. So these are places where hydrogen is will be highly demanded, and that's the reason why we're actually looking into this hydrogen as a thing and
Mm.
how what are the challenges we can face
Yeah.
when we finally adopt it in a full length.
Mm.
Thank you.
Yeah. Yeah. Here in Denmark, we're talking a lot about creating hydrogen hubs and the hydrogen highway, putting tubes in the entire country, producing hydrogen with the windmills on the coastline or in the ocean, and then sending hydrogen through the network out into the country and to Germany.
Mm.
Um, but I also hear that there are a lot of challenges. You cannot use the same steel for the tubes as you do with natural gas. So, what is it that hydrogen can do to metals that makes it difficult?
Yes, sir, thank you very much. That's another excellent question. You see, in the field, in the technology field, they call something a repurposing pipeline, right? So it simply means they want to use, I mean, people are deliberating on using the existing pipeline that we use to transport our natural gas to
Mm.
transport hydrogen. But then we need to understand what exactly, how does hydrogen interact with metals? That's the first step. When we understand the mechanism, then we'll be able to go into details in trying to qualify some materials and try to disqualify some materials. So in a
Mm.
nutshell, you see, hydrogen, as you have said, it's a very light, very tiny atom, right?
Mm.
So, and it has its own special way of interacting with metals. Because of its lightness, it diffuses very fast. So
Mm.
it simply means it could get into the lattice site of materials, right? So, for example, when we use steel, so what happens is that the way it interacts is hydrogen looks inside the material it's diffusing in and look for spots that's suitable for it. And
Mm.
where it likes to stay are high stress points where we have some defects, dislocations, where we have some pores, where we have some cracks, and things like that. And for example, when you look at high strength steel, for example,
Mm.
what makes high strength steel to have this strength is because of uh, dislocation density, right? So
Mm-hmm.
it's high. So there are a lot of dislocation areas where dislocations actually are in this material. So when hydrogen enter into high strength steel, for example, he's very happy because there's so many places he could stay. And what happens is that then it pile up in those places and stays and accumulates. When it accumulates in those places, then it causes a kind of at low temperature, it causes a kind of internal stresses, and then it begins, which could actually ease crack initiation and propagation, and then we have the failure of the material. Also at high temperature, when you have an high temperature, steels actually naturally at high temperature they are immune to hydrogen embrittlement because the temperature is high enough, the hydrogen will diffuse in and diffuse out, right? But there's something that actually happens in steel when hydrogen goes at high temperature. So what happens is that it can also react with the carbon in hydrogen in steel and
Mm-hmm.
and forms a kind of a methane. And methane doesn't diffuse. So what happens is that metals then percolate and fill the microvoids in the steel. And then
Yeah.
as it increases the internal pressure. And
Mm.
as it increases, it causes blistering. Then we have the localized swelling that you can see
Yeah.
in steels and things like that. And before you know
Mm.
it, you have a material being damaged. So these are ways. And if I have to go a little bit more technical into it, so
Mhm.
there are some mechanisms that actually, researchers and simulation have actually brought forth like an argument on how
Mm.
hydrogen interacts with metals. So, for example, it interacts with dislocation. So, what it does is that it forms a kind of a cloud around a dislocation. And when it forms a cloud around it, what it does is it reduces the stress field around the dislocation. So when two dislocation are side by side, they repel because of the stress field.
Mm.
But what hydrogen does is that it reduces the stress field and makes those dislocation more mobile. So we have dislocation glide. And what happens? And it causes plastic deformation and crack is being initiated and crack propagates from there.
Mm.
That phenomenon, that mechanism, people call it hydrogen enhanced localized plasticity. So that happens when
Mm.
hydrogen concentration is low in the material. So another mechanism that was brought forth is also hydrogen enhanced decohesion. So this is that hydrogen goes into in between two atoms, or where there is grain boundaries,
Mm-hmm.
or where there are precipitate interfaces. Then it stays there, or cracks, it stays there, and it accumulates. So as the concentration of hydrogen increases, it gets accumulated. So what
Mm.
happens is that it reduces the activation energy between the interatomic bondings between these two atoms, and so therefore at a point the atoms begin to dissociate for themselves. So the bonds get reduced and we begin to have crack initiation and
Mm.
they propagate and we have failure. That's the second mechanism. So the
Mm.
third mechanism, they call it hydrogen-induced stress, hydrogen-induced stress intensity vacancy formation, HESIV. What happened is that hydrogen is in a material, right? So
Mm.
when there is a little bit dislocation, hydrogen moves and creates a kind of vacancies, right? These vacancies accumulate to create a kind of a micropores in the material, and these micropores can also accumulate to form a bigger void, and which actually hinders dislocation movement, and then we have failure. Right.
Yeah.
So these are some mechanisms that
Mm.
the way hydrogen interacts with metals. And when we understand that, we'll be able to now see what can we do in order to reduce or to mitigate this effect. For
Mm.
example, even with interaction with dislocation, there is also a special interaction of hydrogen with some individual elements. It has been proven that Manganese, for example, loves hydrogen so much that the moment it
Mhm.
sees hydrogens, it gets married to hydrogen. So it
Okay.
means that it traps hydrogen locally. So it takes the hydrogen and hydrogen cannot move again. And
Mhm.
that's what we call hydrogen trapping. So
Yeah.
if we can have that, that means we have so many materials like that. I mean, materials with manganese,
Mm.
it looks for the hydrogen and traps the hydrogen. Then we can mitigate hydrogen embrittlement because there are two ways in which hydrogen can be trapped. We have the reversible and the irreversible. We want the irreversible where it's
Mm.
permanently trapped. But the reversible simply means when there is a little agitation, hydrogen can be released from where it's been trapped and
Yeah.
cause some kind of chaos somewhere else. So these are some mechanisms that we actually need to understand
Mm.
before we can start designing materials and we can start saying that, oh, we can use this pipeline to transport hydrogen or
Mm.
not, because it's very critical. Because
Mm.
most of the pipelines, when we designed the pipelines in the 18s, right, we don't have hydrogen in mind. We never know that we'll come to a time that decarbonization will be something of importance, right?
Mhm.
So we have some high strength steels in those pipelines, right?
Yeah.
And then just imagine we're now using it to transport hydrogen. There
Mhm.
will be a lot of issues. So
Yeah.
these are things that we're actually looking into, and
Mm.
this is how hydrogen interacts with steel. Thank
Yeah.
you.
So two reflections. Um, the manganese. If I add manganese, it could save the world in this matter. And the second is all the failure modes you talked about are in grain boundaries or if you have defects. So if you made single crystal, you cannot have hydrogen problems. Is that right?
No, you are right and you are wrong as well. Because,
Yeah.
for example, in nickel base, single crystals, for example,
Mm,
that you have a single crystal does not mean you don't have some regions that are high stresses, right?
mm,
We talk about the gamma prime and the gamma and the gamma prime in
yeah.
nickel based superalloy, for example.
Hmm.
They are single crystals, but
Yeah.
these are the two phases that dominates nickel based superalloy.
Mm,
The interface between the gamma and the gamma prime could serve as a place where hydrogen can stay and relax, right?
mm,
And then also there are precipitates forming also. So if you have a very good heat treatments and then you try to minimize the segregation and things like that, but
mm,
then there are still some little defects there.
yeah.
So where
Mm,
this is where hydrogen looks into and say,
mm,
I can still come in here and create havoc.
yeah.
So
Uh,
you don't really save the whole world if you go into just single crystal. You
okay.
It could minimize the work. It could minimize the work of hydrogen, but
Mhm.
that does not mean hydrogen enrichment cannot happen.
Okay. But then are there differences in the crystal structure? So if I go ferritic or if I go austenitic or if I go magnetic, I could imagine austenitic is hard. And if it's already brittle, it as you said, high strength steel is an issue. But how does structure, the crystal structure themselves, is the lattice distance, does that play a role if you have FCC, if you have BCC?
Yes, it does. It does plays a role. What we are talking about is more of the overall effect. For example, in
Mm,
high entropy ship memorial, high entropy alloys, majority, all, don't let me say all, but majority of high entropy alloys, they are FCC.
yeah.
And then they are stable. So FCC is very stable. And
Hmm.
then there are arguments up and forth, like because of the FCC nature of high entropy alloys, that's the reason why they have an inherent resistance to hydrogen embrittlement. But that's not the main reason,
Mm,
right? It could be part of it. There's so many other things. For example, in high entropy alloys as well, the way plastic deformation happens in high entropy alloys is a way to accommodate more deformation. So we have phase transformation there. We have twinning in high entropy alloys. So
hmm.
this could also plays a role in resisting hydrogen embrittlement. So there are a lot of nuances in it. So yes, structural FCC from research, yeah, FCC is a stable phase. So yes, it could actually have a standpoint in resisting hydrogen embrittlement. But then in the FCC, if we have a lot of defects, the process of the manufacturing process of the material itself plays a bigger role. From my own point of view, I think that plays a bigger role because in the manufacturing process, that is where the material inherits its primary features. Dislocations are being inside, pores, and things like that. So I will say let us look more into the processing because processing brings about the high strength steel. It's by processing, right?
Yeah.
So then we have to look into that. And we now understand that these and these could enhance hydrogen embrittlement. These and these could actually make it worse. So then let us minimize this. For example, low strength steels and medium strength steels, ASTM actually recommended that because there are less dislocations in them. It simply means there are less room for hydrogen to stay and sleep and wake up every morning.
Yeah.
So that's so these are the nuances in it.
Yeah. Then I would like to talk a little about temperature dependence, and I have two backgrounds in this. In my daily life, I am centering stainless steel. We are centering both austenitic and ferritic grades, and we center in pure hydrogen. So we have 100% hydrogen atmosphere at 1150, 1200 degree. But we never see hydrogen embrittlement in our parts, even though they're very porous and hydrogen is all over it while we're sintering. Is that because at this temperature, hydrogen can go in and out? It's just like an open house without window.
Yeah. That's one of the major. That is one of the major ways. Let me talk about the hydrogen at high temperature in steel, for example. It's basically because hydrogen have enough energy to diffuse, so it spits in and spits out, right? At that high temperature. But remind you, it's not only hydrogen embrittlement. We have another thing called high temperature hydrogen attack. Now, this is totally different from embrittlement because embrittlement causes failure by initiating cracks. Now, in this high temperature hydrogen attack, we have something we call hydrogen embrittlement, hydrogen reaction embrittlement. For example, in steel, or let me say in nickel-based superalloy, for example, hydrogen goes in and reacts with nitrogen and with nickel and forms nickel hydride. These are brittle phases. So when it forms at the grain boundaries. And when that happens, external stress on the material creates cracks right at the brittle phase region. And then we'll begin to see propagation of those cracks. So this is an example of what could happen at high temperature. For example, I mean in HDI, HDI, right? HDRI, they don't really face hydrogen embrittlement at high temperature because there is high temperature. But what they face is hydrogen reaction embrittlement, because then hydrogen reacts with carbon. Then it forms a new compound called methane, and this methane causes blistering, especially in the walls of the in the walls of the reactors, in cold spots and things like that. So in your centering, probably the processing plays a role. Probably the time for your sintering plays a role. Probably, for example, don't let me say 100% sure because materials differs in whatever. But if, for example, in the process of sintering, you shut down your system for a while, and then you reduce your temperature to some certain level around 200-300 degrees C, then you fire it on probably the second day. I'm pretty sure that you will see regions where you see your hydrogen saying that I am welcome now because the temperature the temperature is now okay. I've reacted with some of your elements. Now I am here. So that plays a major role. So temperature plays a major role because the driving force is diffusion, right? So and yeah, exactly. So it's material we react at different ways with hydrogen.
Yeah. But if we look at the furnace, the walls in the furnace are built in the ferroalloy material, so the iron, chromium, aluminium. So when it gets hot, and we oxidize it prior to using it to build up this oxide, aluminium oxide film to protect it. Is the diffusivity of hydrogen stopped by this layer of aluminium oxide, or can it also penetrate through that?
Yeah, one thing about hydrogen, aluminium oxide with hydrogen is that aluminium oxide has a less solubility for hydrogen. So they have an inherent resistance to hydrogen. So it means that hydrogen diffuses in and out of aluminium oxide irreversibly. So it does not mean that it doesn't, but it doesn't stay because aluminium oxide has a very low solubility for hydrogen. However, there have been reports that there are some hydrogen damage in some aluminium alloys, and that is strongly attributed to another mechanism which is totally different from hydrogen embrittlement, and this is hydrogen reaction. So what happened is that if hydrogen managed to diffuse into aluminium through aluminium oxide, and there are some defects at the subsurface of the aluminium oxide, hydrogen percolates there. And it gets to a point that hydrogen begins to build, and then the internal pressure builds up, and then we have this kind of blistering. So majority of hydrogen damage in aluminium alloys are strongly related to hydrogen blistering. So we have this localized swelling and then it blisters. So it simply means this is totally different from the hydrogen embrittlement we know about. So because aluminium oxide has a very low solubility for hydrogen.
Yeah. So if you can have a stable, strong, thick layer of aluminium oxide, that will be the barrier reducing the risk of blistering.
Exactly. There's not much of a report of hydrogen embrittlement in aluminium alloys.
No. Now, digging into this hydrogen DRI, there are different technologies. Some runs at ambient pressure, some runs at 810 bars at 950 degree with hydrogen in massive amount. Does pressure do anything to harm the material, or is it independent on the hydrogen pressure?
When you talk about pressure in the whole process of HDRI, it's more effective in the reaction time, because the main idea is hydrogen goes in and reacts with the iron ore, right?
Yeah.
So when you increase the pressure, so it simply means you destabilize the equilibrium reaction.
Yes.
So it goes to the production side. So you produce more metals.
Exactly. That's the purpose of it.
Exactly. So when you reduce the pressure, you begin to form more of the iron and more of water. Why? Because then you shift the equilibrium reaction. So and that alone. So if hydrogen is affected by the pressure. So it simply means the same, almost the same influence of temperature on hydrogen is also on the pressure on hydrogen. So for example, when you look at when you increase the pressure, the reaction increases. So hydrogen have a very small distance to cover in reaction with the pellet, right? And then it diffuses into the pellet, and you begin to form your hematite to magnetite, then to iron oxide, then you have your iron, right? And so this is actually what actually plays a role. So the most important what can I say? The most important factors in HDRR are temperature, pressure, the time itself. The time itself, because for every technology, you must be economical. You must be economically wise about it. If the time you produce your iron is far more, you are running on a lot of electricity, and then the cost increases. So you have to reduce the time. So if you have a shorter time, less consumption of electricity, and then your product will be cheaper. And we all want the product to be cheaper now, because HDRR ions, they are very expensive right now. So these are some things that we'll look into. So hydrogen pressure plays a role, temperature plays a role, time plays a role.
Yeah, wonderful. If we look back into these problems we talked about with pipes made of the wrong material, what do you see as the task we have in the society ahead of us to have a stable hydrogen environment, or with other words, what will be the consequence if we don't handle it?
There are a lot of challenges, actually, and that's the reason why the adoption of hydrogen has not gone so far, right? Because there's so many nuances we actually need to examine, especially in the research field. So, for example, as you're talking about repurposing of pipelines, some suggested that, okay, why can't we reline the pipeline? Then we look at how many pipelines are we going to reline? That is a whole lot of cost, right? If we have to change the whole pipeline, is a whole lot of cost. And then in mixing, some said, okay, some have been mixing 20% hydrogen, 80% of natural gas. Yes, that is okay, but we are still at the risk of hydrogen embrittlement. And also, we are not, if we have to do that, then we are not going zero emission. We are just reducing the emission. And then when we look into it more critically, there is something we call the Wobble index. So this gives us it gives us the knowledge of, okay, when we mix this natural gas with this gas, we can still use this for this pipeline. Now, if the Wobble index between the two gases are very different, then it's an indication that we cannot use this the pipeline, because the risk theory is that we could, for example, for our burners, we could have overheating temperature, or we could have underheating temperature. But there's something more critical about hydrogen, is that it is low energy volumetric material. So it simply means if we want to increase the volume of hydrogen, you need a lot of compressors.
Yes.
The energy of hydrogen needs a lot of compressor, because you have to compact it. Major challenge of hydrogen.
Tanks.
Exactly. Or build tanks. And then and these are major challenges. See, I'll tell you something. The efficiency reduction of hydrogen, the transformation of hydrogen from one form to another, the supply chain takes away 60% of its efficiency. If you have to produce hydrogen, it loses efficiency. You compress it, you are putting more energy at a lower efficiency rate. Then you convert it back to electricity. At the end of the day, you have like about 30 to 40% efficiency, compared to battery that is about 70 to 95%. So these are some challenges. Another challenge is we have to look into the policies and standardization. In the field of metals, we have the ASTM, we have the ISO, for example. So they tells us this is how you produce your titanium, this is how you produce your this, right? that also needs to be done for hydrogen. We're supposed to have a standardization. This is how we produce hydrogen, this is how we handle hydrogen, and this is how we store hydrogen. Don't forget as well that hydrogen is highly flammable.
Yeah.
So we need technical know-how. We need to build people. We need to train people. And this is where industry needs to come in. Take so many guys, train them in this way of hydrogen, because we need to do that, because something that's highly flammable, security and health, it's an important thing that we need to look into. So these are some things that we actually need to look into. Also, when we talk about the industrialization processing, how can we adopt this process? How can we design our reactor? For example, one important challenge about HDRI is the demand for high grade of iron ore. And for the production of iron ore, less than 5% of iron ore we have that kind of high grade.
Yeah, it's there are a lot of slack in
exactly. And I quite understand that, because the processing of HDRI is totally different from BF or BF-BOF, because you heat and then you melt in BF, but here there is no melting. You do everything below melting point. So it simply means every impurity that sticks to the ore stays with it till production, and that reduces the quality of our steel. And then if we now have to transfer the HB which is the hydrogen Bernoulli's iron, to the EAF, which is the electric arc furnace, then we need to consume a lot of electricity for us to melt the impurities.
Okay,
and
so
for it
that's,
so this has some things that, how can we design a reactor that can accommodate a lesser grade iron ore and yet still produce high quality steel as that of BF? How can we optimize the electrolyzers of green hydrogen, for example? They are very expensive. We use iridium, platinum in part of these electrolyzers. How can we optimize it? For now, we have about $4 to $6 per kilogram of hydrogen, which is like about 3 or 4 times more expensive than a crude oil, right? We need to break it down. Though, actually, there are many improvements. Since 2020 to 2024, it reduces for about 60%. And we can still go more, because there are a lot of flashlights into research now. And people are actually dipping into a lot of research on how to optimize electrolyzers. This is a good side, but we still need that reduction. So these are challenges here and there that we have to. We have the challenge of hydrogen embrittlement. We have the challenge of high grade ore. We have retrofitting. For example, if I'm using BF-BOF plant, and then you ask me to change to HDRI, am I going to abandon? Am I going to abandon my plans, right? And then go for. But if we have a situation whereby the process is being optimized in a way that we can still use, we can retrofit the BF to HDRI. I mean, it's going to minimize a lot of cost, and we're still going to use a lot of elements. So these are so many things, really so many things. And if we don't see into that, I'm afraid we will not be able to fully adopt the potential of hydrogen, because we need to settle all those questions before we can. I mean, investors can come in and pump. Yeah, there are a lot of money pumping into it, but we still need more, and there is possibility for more.
Yeah. What is the efficiency of state-of-the-art electrolyzers today?
Presently, we have we have 2 to 3 types, but 2 main ones are going on now: the IEL, which is the water electrolysis, and the PEM. And the water electrolysis is about 50 to 60% efficiency, while the PEM goes from 70 to 85.
Okay. So there's also a loss there.
There is a big loss. But people said there can be improvements, which I believe as well there could be improvements, but it's going to take time. But bigger than the improvement, I'm still looking at the materials we use, especially in the PEM. We make use of iridium, platinum. These are rare materials.
Yeah.
So when we begin to push forward hydrogen and people begin to buy into the idea, we need more electrolyzers, then we need more miners to mine a lot of iridium and platinum. So do we have sufficient iridium and platinum that can sustain the market value of hydrogen? A big question that we need to answer.
Yeah. Okay. So if we look at this, hydrogen can be a transformation technology. Do we historically have situations similar to this we can lean on, we can be inspired from, where it could be cases where it went wrong, or it could be cases where we succeeded?
Yes. I mean, the one that is coming to my mind right now is the Liberty ship. You know the story of the Liberty ship in World
Yes,
War
I
II?
do. Yeah, those that broke.
Yeah, it's really. I mean, you when we learn from it, we notice, it's because of the urgency of the war. Then they begin to produce a lot of Liberty ship,
Yeah.
and the design for the Liberty ship is one problem, and the material they use is another problem. At that time, we have little knowledge of brittle to ductile transformation. We also have little knowledge of welding technology, right? So
Yeah.
it's more of the holding, riveting, bolt and nut for creation of machines and things like that. So, but because of the urgency of the war, we deploy this new technology without having an in-depth understanding of it. So we produce about almost 2,000 plus of ships, and within 1 year, over 1,000 ships were wrecked, and the cause of damage was based on brittle fracture. I mean, they begin to weld steel materials that doesn't have good weldability. So at lower temperature, we have these micro cracks from this weld area begins to grow, and because the material transforms from ductile to brittle at lower temperature, so this ductile brittle transformation, and that actually caused about 1,000 shipwreck, right? And it's as a result of we don't really understand the technology behind this, and that will actually give birth to fractography. I mean, this fracture intensity, fracture intensity, I've forgotten the name. I mean, this critical point, I mean, this value, we begin to measure this fracture intensity of material. If it is bigger than the fracture toughness of the material, it means that the material will fail. But we learned that from a very bad experience. And that was the lesson they taught us. And this, if we have to apply this to hydrogen, so it's trying to tell us that let us be in a haste in doing a lot of research in hydrogen, but step a little bit down in adoption of hydrogen. Let us first of all master the act first before jumping into the ship, because so that we will not replicate the same history we made with Liberty ship.
Yeah, so we have to invent the sharp EV test for hydrogen before we build.
Exactly. That's the lesson there.
Yeah. So I think we have come to an end, but I would like to have your point of this is everyday metallurgy, so it also have to reflect how does it affect our daily life. So if I have to tell my kids and my mother, how can the hydrogen era affect her life? Is that something she could feel when we are there?
Yeah, definitely. I will try to tell a story of we trying to one time want to go to Mars because this Earth is almost being destroyed by emission of carbon. But the moment we adopted hydrogen, So we begin to reduce our emission, or probably we bring it to a very low or zero emission, and we begin to have faith in this planet again. And they said, okay, no more, we are not going to Mars again. We are going to stay here, and then we're going to reduce, or we are not going to emit any emission. And because of this little atom called hydrogen, it's going to affect every aspect of our life. We can have modular electrolyzers, we can have a lot of efficiency in hydrogen, we can have, it's going to change a lot of things in our manufacturing industry. So we can say before, oh, we have to queue and buy fuel. But now we have a very fast charging point because we are using hydrogen. These are things that affect our daily life. Produce more jobs is going to give us another way of metallurgy, for example. In we are going to dump the old way of we have to heat to this high temperature, and then we'll be scared of the melting point of the liquid and whatever. Now we have electric arc furnaces and things like that. It's going to produce a lot of jobs. It's going to produce a lot of metallization. We're going to increase the production of steel and things like that. I think these are ways that hydrogen technology is going to affect our daily lives, especially also when it comes to storage and things like that. So these are ways these are the stories we can tell them.
Yeah. And you could say if we compare to oil, there are some geographic regions in the world where oil is concentrated. If we go to hydrogen, it's based on water.
Yes, and
it's
then
all over.
Yeah, we can just say, you see, before there are some countries that are very rich because they have a lot of oil, but now all countries are rich because everybody have water.
Yeah, exactly. Yeah.
Exactly.
So it will be a peace bringer to our world.
Exactly.
Yeah.
I strongly look forward to that era where we're going to be using hydrogen. And the same water I'm drinking is the same water that is providing electricity for me, is the same water that is providing the metal I'm using, is the same water that is providing what I can use to charge my phone, what I can use to charge my car, and things like that. Then we are going to put a lot of value into the same water we are wasting. Then we will not waste it anymore.
Yeah. Wow. I really love that ending. So thank you very much. I enjoyed the conversation. I learned something new about how it penetrates and where it looked for dislocations. So thank you for opening my mind on the hydrogen again.
Thank you very much for bringing me to this platform. I also enjoyed this conversation. You're such a nice, cool person that we can go on and talk more about so many other things. You're really, really a nice person, and I'm really happy that I come on this platform today.
Yeah, thank you. Enjoy the day.
Okay, and you too. Thank you.
Yeah, bye.
Bye.
Hi, everybody. Thank you for following this episode on hydrogen. It was fantastic to learn about how it could penetrate all kind of alloys, the reference to the liberty and learning from that. I really love that. And the final story about how the future could be hydrogen based, creating peace in the world. I really like that. But hang on, because next episode will be about how to measure the chemical content of steel and alloys. And one of these material that you want to measure is hydrogen, because hydrogen can make a mess. And if you're not able to measure it, then you have some problems. So stay tuned. Next episode will be with a specialist from LECO, the company that makes the equipment to measure chemical content of mainly steel. See you soon.